Yeah, good evening, everyone. Switch on your cams. Let's start off. Chalo, cams on, everyone.
Yes, sir. 1 second.
So the last thing we were doing is this. Yeah. So last thing we did was this. The height of the capillary is given by 2s cos theta rho gr, right? And we proved it in two different ways. One is the pressure method and one is the force method. Then, so when I was learning this thing in school, right? So my teacher has taught till here exactly. And he said we'll continue tomorrow. Then after seeing this thing, right, I got a brilliant plan. Right. The plan was like, I thought I will take a container, okay, and I'll put a lot of capillaries like this. Now, let's say this height of the capillary with the formula we derived is 2s cos theta rho gr. For example, let's say this is 10 centimeters. So my plan is I will take pipes of only 5 centimeters. Then what will happen? All the water that is filled up there will start coming out. Then I'll put one more container here, and this water will come here. Then I'll put more capillaries here, again 5 centimeters. Again, the water will come out. Again, I'll do this thing. The water will come out. Eventually, once after reaching certain height, I will send the water through this plane and I'll run an hydro power plant, and I'll produce electricity. The water will come down and again will go up. Did you get the concept? The height of the capillary, if it is 10 centimeters, I'll put only 5 centimeters. So the liquid will start oozing out and gets collected in the higher container. I will keep doing this till I get enough height. How is the plan? So using this plan, I calculated completely how much capillaries I need, how much water I need. So I sat down, I took 3 4 A4 sheets and I made a full plan. So I made a plan to, become the world's richest man. The free electricity, right? I thought I'm going to open a power plant and I'm going to sell this electricity. So अच्छे से proper plan लिख के everything was done and I was ready to get a patent. So next day I went to school, 11th standard class, and I was waiting अभी teacher आएगा. After the class I will show him. And then once he says okay, so then I will ask him how to get a patent and we'll start the company soon. This was the plan. This is what happens when you don't have, PUBG, Instagram, internet. So kids, we do all weird things. So ho gaya tha, I went to the class and my friend saw the sheets. I said, Arun, Arun, kya hai? I said, kuch nahi hai, nothing. I'm not going to show you because what if you steal my plan? And then you say it is mine. So you have to be careful with this thing. So then the class, then I said, okay, I was completely excited. Right? Abhi class ho jayega, class ke baad, then I will show the teacher and ready, like done. हो जाएगा करके then next day patent आ जाएगा 1 month में factory start हो जाएगा and there I'll be producing a power plant. अभी सिर्फ ये doubt था power plant का नाम क्या रखना था. That was a confusion I had. So but I thought okay चलो class के बाद सोचते हैं वो सब power plant and then the class started. Then the teacher started with this topic. Tube of insufficient length. So first thing what happens if you take a pipe, let's say you're getting 10 centimeters from the formula but you took only 5 centimeters. First of all, the liquid does not flow out. We'll see why. The liquid completely fills the tube. And does not float. That is the first thing, right? I was stunned. I said, "ठीक है, teacher can be wrong." So then this is what was happening. Keep your cams on, everyone. Bye. People are missing today. So if you take let's say capillary there, and if you take a capillary here, so let's say the liquid normally would have gone till this height. This is a normal height. But if you take a pipe lesser than this, we observe the liquid will just reach here and there's no overflow. The reason is this. If you look at the FBD here, you will clearly notice the reason the water is going up is because this liquid is getting attracted like this. The adhesive forces, the solid is actually attracting the content liquid, right? These adhesive forces are responsible for the liquid to go up. Now, if when you take a tube of insufficient length, how are the forces? Even the adhesive forces are also down, isn't it? These are the cohesive forces. There is no surface only on above the liquid in order to pull it up. The reason why the liquid is going up is because the force between the liquid and the solid is stronger than liquid. The molecules are being pulled apart by the solid which is on the top of the surface. But if there is no surface on the top, what would happen? There is liquid doesn't go up only. You need someone on the top to pull you up, isn't it? So there is no surface. Since there's no surface, solid surface on the top, there is no attraction force. There is no upward force. Actually, in return, if you try to go even higher, the surface tension pulls up. Remember, I said it is like a membrane. If I try to go out, the membrane will still stretch in the opposite direction. If liquid tries to go out, the surface tension actually pulls it down. I'll show you how it looks. Can you see how is that liquid there? So if you try to pour more liquid on the top, this is what is actually happening here. The surface tension is actually pulling like this. It's like a membrane there. This is how the surface tension is pulling. So the net downward force will be 2 pi rs cos theta. This is what happens. If you try to overflow, since it's acting like a membrane, it won't come out. You have to apply more pressure for this bubble to pop up and then the liquid will flow. Clear how the diagram looks? So simple thing. Since there is no one to pull you up, the liquid will just rise till that height and you'll stop. The formula is still valid. The formula mein h dash will change. So 2s, this also becomes cos theta dash by rho gr. The contact angle changes. Since the edge of the surface is different, it has a different contact angle. So the formula is still valid. Contact angle will change and the height will change. Clear with this? So this is what the teacher taught. I took those papers and kept them in the dustbin. So that is how my entrepreneurial journey has ended. Then my friend came. I said, "What happened?" Was I said, "Le lo, do festival." Who thought a tube of insufficient and can do this much? So literally, what I've created is a what do you call that? We call it perpetual motion engine. Ever heard about it? A perpetual motion engine is it's an engine which does not require any input energy. There's no input, but the output keeps coming. Basically, law of energy, conservation of energy is not valid. Such things can't exist. And I was trying to make one. Clear? Next thing. So in this process, we also have some heat produced. Now see, in this capillary there, the water level has gone up to a certain height. So this force would be the surface tension is pulling this way. So we have a vertical component here, 2 pi r is cos theta. Yeah, height always we take it from the lower part. We ignore that sides there. So this vertical component would be 2 pi r s cos theta. So the work done by the surface tension force is force into displacement, which is 2 pi r s cos theta into h. And we know the center of mass of this liquid is in the middle. That is h by 2. So change in gravitational potential energy is mgh by 2. But we also know from equilibrium 2 pi r s cos theta is equal to mg. So that means the heat produced, so this is nothing but mgh. Therefore, the heat produced in this. So whenever you put a capillary and the water level rises, there is always some loss of energy. The work done. So I did a work of mgh, but you stored only mgh by 2. So what happened to the remaining? It must have become heat. So half of the energy becomes heat. You will notice this, and this is a very common thing in physics. Later on, we will see this in current, electricity, capacitors. We will see this thing in elasticity. For some reason, always that half of the energy keeps going off. Yeah, the H's height is measured from the meniscus to the meniscus ka bottom to the surface level. There. So whenever you use a capillary, there is some heat produced. Clear? Let's see some questions. Rehan, your cam is blank, right? So we have a liquid here. And we have a capillary here. The liquid level rises here to height h. This is the height of the liquid column. L is the length of the complete pipe. Now what we did, the pipe is removed. The capillary is removed. And the liquid is removed outside. Liquid is poured slowly from the top. Meaning you took out that capillary ka thing. And then from the top, slowly you started putting liquid. And we observe the liquid starts getting accumulated in this. Liquid doesn't fall. Getting it? There is nothing here. There is just air. There is no container. This h dash is the height of the column. Find h dash.
H dash is like the maximum height
Yeah,
which
find
can be
h
held
dash
in
is
the
the
capillary, right?
right. Let me write it as find maximum height of the liquid column. What is the answer? So when you kept this pipe in the liquid, you got a height h. When you took it out and then you poured liquid, you got a height h dash. I didn't give you any values, right? S, rho, G, nothing is given. Only H is given and L is given. Your answer should come in terms of L and H only. There is no other data that is there. Yeah, I'm asking you to find H dash in terms of H and L, not ratio. Go back to the basics. Why is that liquid rising in the first place? There was this meniscus, which is pulling with 2 pi r s cos theta. And because of that, you got the height h. Now, when you have taken it out and you pour liquid inside, you will have one meniscus here. You will have one more meniscus here, isn't it? Isn't this how the liquid will be? There'll be two meniscuses. So this guy is pulling up. This guy is also pulling up. So there's an upper meniscus and there's a lower meniscus. So we'll have 2 pi r s cos theta. And we also have 2 pi r s cos theta. So there are two meniscuses here. So here 2 pi r s cos theta, right, balances mg. Since there are two meniscuses here, will balance 2 times the height. But we have to take care of one thing. Balance is 2h height. So if the length of the pipe is greater than 2h, then the answer h dash is 2h. If length of this total thing is less than 2h, then h dash is L. Does it make sense? Meaning, take in terms of numbers. Let's say this height of the capillary from the surface is 10 centimeter. And let's say the total length of the pipe is only 15 centimeter. So technically you can balance 20, but the length of the pipe is only 15. So what will happen? You'll balance only 15, right? Meaning the entire pipe will be full. If length is 30 centimeter, you can balance 20 centimeter. So you'll balance 20 centimeter. So it depends on the length of the pipe. If the length of the pipe is greater than 2h, then you can balance 2 times the liquid column. If length of the pipe is less than 2h, you can actually still balance 2h, but your pipe is insufficient, so you balance L. Is this clear, everyone? So the main idea here is we'll get two meniscus here. Simple reason. This is air, that is liquid, one interface. This is air, this is liquid, one interface. Whereas in this scenario, if you see, this is one interface. Here, there is no surface here. This entire thing is liquid only. So we have only one meniscus. Easy? Simple question. Anyone confused with this?
So how will we know that the bottom meniscus is convex or concave?
It can't be concave, right? Think about it. If it is like this, meaning this is also pulling down, this is also pulling down, the whole liquid will fall down. Remember just now I said what? It acts like a membrane, right? Don't think of like convex and concave. Think of like this. If you had a rubber band here, if you put weight, what will happen? The trampoline will stretch like this, isn't it?
Yes, sir, got it.
Think of it like a trampoline. When you're pouring the liquid inside, the liquid the surface is like a trampoline. Whether you try to pull it up or pull it down, it is going to stretch, whichever way you apply pressure. Clear with this?
Yes, sir, clear.
All clear this? Next one. Next one. Let's say we have liquid. So the liquid rises to a certain height. This is H. Radius of the pipe is, this radius is A. Now what you did, a rod of square cross section is introduced in the middle. This is what you did. You're getting it? You kept a square rod here. The side of the square rod, side is a by 2. We can take side is a. Yeah. So if you look at the top view, I should have made the rod a little big. Make it a by 2 actually. This is how it looks. Able to visualize how it is? You introduced a rod in the center exactly symmetrically. Now what happens? The liquid level will be between them. This is the new height h dash. A rod of square, you're getting it? So assume the material is same. Assume contact angle and the surface tension is same between the rod and the cylinder. Angle and surface tension is same. Find h nu. So initially when you kept this capillary of radius A, the height of the liquid was h. When you took a square cross-section rod and introduced it in the middle, the height became h nu. Assume the contact angle between the, this pipe and the square rod. The contact angle is same for any surface. Then find the height of the liquid. Into 1 plus 1 by pi. That looks weird. I don't remember the answer, but I don't think that looks right. Did you take the surface tension ka force due to the square rod also? Think 1 minute more, then I'll show you. Just to give you an idea here, the liquid, right? You'll have a surface tension here also. That is also pulling up now. I hope you included that. There's a surface tension force due to the pipe, and there's a surface tension force due to the square rod. Yeah, and you have to remove the volume of the rod. Try everyone, it's a good one. Arjun, clear with the question?
Yes, sir.
Rehan, still sleepy? Switch on the lights now. Go wash your face and come. H nu is 4AH. God, dimensions are not matching, God. Always, before putting an answer, at least check your dimensions. So, if you see the FBD.
So can I get 2 more minutes to solve, please?
Try. By the time I do, you'll get 2 minutes only. just showing the hint anyway. So this is 2 pi r s cos theta. This was your mg, which is rho pi. I took a na. I hope this must everyone knows this thing. Rho pi a square g. 8h by 3, 4h by... How are you guys getting such beautiful answers, right? Lakshika, 6 pi h by 4 pi minus 1. Yeah, I was feeling something like that you should get. So for the second FBD, when you draw, if you look at the square ka thing, right? This is how the liquid will be. You're getting? This is how the surface will be dragging. You're getting? The liquid is pulled up by this guy also. Where this is theta. So we have that is one force, which is 2 pi a s cos theta. And this force will be surface tension into the perimeter, which is 4a by 2 cos theta.
Sir, it would be rho pi a square and g.
It's way over. Now, where will the liquid be? Liquid will be only in this gap, isn't it? Kara, I'll give you a minute now. I hope if you got the question is over. The main thing is this only, figuring out that there are two surface tension forces. One is due to that pipe and one is due to the square rod in the middle. So the square rod in the middle, how will the force be? There are four sides. So there will be four things, going up. Each will have a vertical component of s into a by 2 into cos theta into 4 times. The answer won't come that nice. You should be getting something in terms of pi. So four h into pi plus 1 by pi into 4h minus 1. Okay.
So once again,
Uh,
I mistyped 1 second.
type na. It's okay, Resh. You get it. This thing 2 SA cos theta. This is equal to what will be the weight? Density. Area would be pi a square. Remember, you have to remove that square ka cross section also. So a square by 2. No, you can't get that into h nu into g. Please check the equations. If you got this question over, you got the answer. Now you just have to replace this 2 pi a cos theta here. Now I don't know s ka value now. So a s cos theta would be rho pi will cancel rho a square hg by 2. Substitute here. 2 pi plus 2 rho a square hg by 2 is rho by 2 2 pi minus 1 a square h nu g. A square cancels, g cancels, 2 cancels. We get 2 pi plus 1 h 2 pi minus 1 h nu. Hope I'm right. Did I goof up somewhere?
A square by 4 over area.
A square by 4. You're right. Is this right? 4h pi plus 1 by pi.
I think you missed a term of pi in the denominator.
Yeah. Where check कर लो calculations. I must have goofed up somewhere, but I hope you got the equations right.
So can you explain this 2sa cos theta wala thing?
That is the surface tension force due to this thing, the square. When you keep the rod in the middle, even the rod will start attracting the liquid up, no?
Yeah, right. Got it.
That will be four sides, isn't it? The perimeter into s cos theta.
Right, yeah.
Hi, Ishan, did you find that pi? Where
So
did I
checking,
miss?
sir.
Force due to. Lakshika, where did you mess up? तो 6 आया ना? Anusha, clear with this? All clear with this? It's a good one. So next one. Main thing is that. So here there's only one surface tension force balancing the weight. Here there are two surface tension forces, one in the center due to the square rod and one on the top. We took radius as r. So मतलब A का place में r होगा, but फिर भी cancel हो रहा है ना? It doesn't matter. Yeah. Clear with this? Next thing. Check it out. Maybe I missed up by the calculations. But there, if you got this equation, job's done. I will leave the working to you. Next one. We have a rod with a inner and outer radius r1 and r2. So the inner radius is r1 and the outer radius is r2. This was dipped in a liquid. The surface tension is S and contact angle is theta. Mass of the cylinder is m. This is a hollow cylinder with thickness. Remember, that's how they can say. You can say it's a hollow cylinder with thickness, or you can say it's a solid cylinder with a cavity. Both are same. This hollow cylinder with thickness, inner and outer radius are r1 and r2. Mass is m. Find the external force required to pull the cylinder out of the liquid. So someone decided to pull this guy out of the liquid. Find minimum force required to pull the cylinder out of the liquid. All these are like mensural questions. show you. Let's see what are the forces. So inside we have a liquid. Now see, we are drawing FBD of the cylinder. Now try to understand. If you try to draw the FBD of the liquid, that's what we are drawing till now. This is how you were drawing. The surface tension force was pulling it up. That was 2 pi r s cos theta. Newton's third law, if I'm pulling you up, then the surface tension will pull you down. That means on this guy, the surface tension is actually pulling down. You're getting it? If someone is catching you and rising up, that means you're pulling that person down. So you're pulling the pipe down. So we have a surface tension force here, 2 pi r1 s cos theta. Is that making sense? So the pipe is pulling the liquid up. So liquid is pulling the pipe down. One. Second thing, most people, right, we ignore this thing actually generally. Even though we don't use this, there is a meniscus outside also. There is an outer meniscus. This guy is also pulling down with 2 pi r2 s cos theta. And top of it, you have your own weight mg. That's your F external. So the most common mistake is we forget that outer meniscus. There's a liquid inside and there's a liquid outside. Both of them are catching it and pulling it down. So the minimum external force required will be the weight of the rod plus 2 pi r1 s cos theta, the meniscus inside, and 2 pi r2 s cos theta, the meniscus outside. That's it. Question was easy, but most people forget the second part in the middle. This is an outer meniscus. This is the inner one. Clear? Why is the liquid going up? Because surface tension is pulling up. Surface tension is pulling whom up? The liquid. So by Newton's third law, you should do, what should you do to the pipe? Pull it down, isn't it? You're getting, let's say, Aniket, it's like someone has fallen into the river. You're giving a hand and you're pulling them. So the FBD on this person, F is up. What is the FBD of you? Down, isn't it? All clear with this? Easy? 2 steps. Next one. So let's say we have a U-shaped container like this. Here we have a small hole. And the radius is A. So someone started pouring liquid here. We observe as the liquid is getting filled, it doesn't come out of the hole immediately. If you see here, the liquid actually comes like this. It forms a bubble. Find H when the liquid starts coming out of the hole. S is the surface tension and rho is the density of the liquid. Generally in fluid mechanics, you have seen the moment the water level reaches here, if you put even little more, it should come out. But here the surface tension will block the water from coming out. And you know how it would kind of look like? It's not the exact diagram there. If I went for a blood test and they poke your finger, isn't this how your blood comes out? Or do you get a fountain? Tom and Jerry में आता है fountain, right? Tom gets hit, so you get a fountain of blood. That doesn't happen. So when you poke your finger, this is how the blood comes out like a drop. If you keep pressing it, more and more blood will come, and then the bubble pops and the blood will start leaking. So something similar will happen here with the hole also. You don't get a fountain.
So the radius which you have given A, it is of the hole or of that part of the pipe?
Hole का radius है. Radius of the small hole is it. Pipe का radius you don't need. Two pi a s by rho g. Pi won't come record. See what happens. When you look at the hole, initially, right, the surface will be like this. When you're putting the liquid, it remember it's like acts like a membrane. If you try to push it immediately, it won't break. First, you'll try to stretch. So this is how it would be. Theta and theta. So it is trying to push down with 2 pi a s cos theta. If you try to put more liquid, it will become more sharper like this. But still there is some angle. So basically you're decreasing theta here. So contact angle changes here. And eventually, I didn't draw this properly. Eventually you become a proper hemisphere like this. This is the maximum surface tension force you can get. So as the height of the liquid increases, the pressure increases. Basically, the surface becomes more concave in order to withstand more pressure. Contact angle decreases, and also the radius of curvature also. Because if you try to look at the bubble here, this is how it would look. This is a part of this sphere. This is a part of this sphere. This is a part of this sphere. It becomes like a spherical bubble. It's becoming lesser radius. So at this point, it becomes a completely like an hemispherical drop. So now if you look at the pressure, this is your hemisphere. The pressure is P naught here. The pressure here will be P naught plus 2S by A. So on the other side of the container, where you're putting liquid up to height h, the pressure here will be P naught plus rho GH. Since both are at the same height, the pressure should be equal. P naught plus 2S by A is equal to P naught plus rho GH. P naught will cancel. H is equal to 2s by rho g. Once the height reaches this level, the liquid will pop up, meaning this is the best you can do. This is the maximum surface tension force you can generate. So at this point here, the contact angle theta is 0. We get maximum surface tension force, which will be 2 pi as. Or think the other way around, okay? As the height is increasing, the pressure here, P naught plus 2s by radius of curvature should be equal to P naught plus rho gh. So indirectly, we are getting radius of curvature is 2s by rho gh. As height is increasing, radius of curvature is decreasing. When h is 0, how will the liquid be? If h is 0, the liquid will look like this. The liquid is almost flattish. R is infinity. If you put more liquid, it will become like this. You put more liquid, it becomes like this. You put more liquid, it becomes a hemisphere. You try to put more liquid, this is the best you can do. The liquid will pop. Are you clear how the curvature will keep changing? So the radius of, they can ask you theoretical questions like this. As the liquid is poured, what happens to the radius of curvature? So if you want radius of curvature, no? This is your radius of curvature. This would be your angle. That would be your A. R cos theta is small a. R is your radius of curvature. Theoretical questions. Easy. The same question you can ask in another way. They will say we have a container with a hole. And this is pushed inside a liquid. The idea is the same. Container with a small hole. Is pushed inside the liquid. And then you will observe the liquid won't come out immediately. You'll get a bubble like this. So here the pressure is P naught. Here the pressure is P naught plus 2s by A. And from this depth h, the pressure here is P naught plus rho g h. The answer will come same. H is equal to 2s by rho g A. Clear with this? So the question can be asked either way. You can say it is like this. A U-shaped pipe is there with a small hole, or you can say there is a container with a hole and you're pushing into the liquid. So at this height, the liquid will start coming out. So this is an alternate question, same model. Clear with this? Please check the steps. Ask me if you're confused. Next one. Anusha, Adrit, clear with this? Partika? Clear? Pastika? Vidyut? Palaksh? Next one. We have an eyedropper. It looks weird, but yeah, it's an eyedropper. So there is some solution inside here. And when you press out, what will happen? You get a liquid drop. Radius is R. And radius of this hole is small a. And R is much, much greater than A. So assume the hole is very, very small compared to the radius of the drop. R is the radius of the liquid drop. S is the surface tension of liquid. Rho is the density of liquid. Gravity is there. Find R when the drop gets disconnected from the dropper. So basically, ever thought about this thing? When you go to a doctor, right? He says, put 2 drops in the eye. But tell me one thing, you're not supposed to say like that, right? You're supposed to give a proper dosage, isn't it? When you're putting a medicine, you need a proper dosage. But the doctor will simply say, like, put 2 drops or 3 drops. So that means the company which is making these bottles have to design them in such a way, whenever you press, only 1 ml of drop should fall. Isn't it? So the company has to design the bottles, and the medication company also has to design the liquid in such a way that whenever you press, when the volume of the drop becomes 1 ml, it gets disconnected. You can actually design this. So there's no need for the doctor to tell put 2 ml or 3 ml, right? You can't put the solution in a spoon of 1 ml and put it in the eye. It doesn't make sense. So find R when the drop leaves the dropper. Anytime if you see eye drops, right, in that actually 1 to 2% is the active ingredient. Remaining 98% is just a base solution, which is actually used to manage the density, surface tension, for solubility in your eye, all that stuff. And that the active ingredient is only 1%. Remaining is just there. So that is the difference between a person, right? Let's say tomorrow if you have a factory which is making, plastic water bottles, and tomorrow you suddenly decided to make bottles for medical companies. It's totally a different ball game. Even though it looks like you're making bottles for a medical company is much more precise and more difficult, even though both are in the same plastic industry. The Holker radius is so small, so we can assume the drop is almost spherical. In real life, the gravity bends it, but we ignore it. Cube root of 3a(s)(2) rho g. Okay, we have one answer, but I'm not sure. Let's see. You actually get a fourth root, right? You'll actually get a fourth root. Let's see. Draw the FBD of the drop. Again, I'm exaggerating this figure here. So if you look at the surface tension here, it's like this. So the vertical component will be 2 pi a(s) cos theta. So when it is hanging, right, the surface tension is pulling it up with this. The weight is mg. Now here, if you look at the geometry, this is R, that is A, and that I should actually put it, the red, this force is perpendicular to this green line actually. Basically, this green line, that are like perpendiculars. So this is 90 degrees. So if that is theta, this is 90, this is theta, so this is theta. So if you look at the triangle there, this was A, this was R, this was theta. I think I'm goofing up the theta part. I'm goofing up. If that is theta, this is 90, this is 90 minus theta. That means this was theta. Therefore, cos theta is A by capital R. So here the surface tension force is 2 pi A S cos theta. So basically, you're just hanging onto that small hole. Is equal to mg. M is nothing but rho into 4 by 3 pi r cube into g. 2 pi A S cos theta is again A by R. Rho 4 by 3 pi r cube g. Pi goes off. This side it will be 3 by 2 A square surface tension by rho g to the power of 1 by 4 is R. Check. Yeah, that is theta. Right, Lakshika. I messed up that angle. That is theta. Where did we use? You are ignoring this part of the sphere, na? You can't take 4 by 3 pi r cube, isn't it? If that A is not small, it's not a full sphere. You have to remove this volume then. You can't write 4 by 3 pi r cube directly. Clear?
Okay. Yes, sir. Clear.
So there is actually power 4. Next thing. Same question, another way you could have played the same thing. We have a pipe here and you're blowing air with speed v. In this process, what will happen? You'll get a soap bubble. You must have played this thing. Of radius r. So the same question here. Find r when it gets disconnected from the pipe. If you keep blowing right continuously, at one point it comes out right. Find r when the soap bubble gets disconnected. The concept is the same. There it's from a dropper. Here it is this. But here the catch is when you take this bubble, the forces will be the air is rushing and hitting here. Remember rho a v square? That will come rho a v square, where a is the area of cross section of the pipe. Let's say this radius is small a. So here a will be pi a square. Let's say r is much greater than a. So here we also get the same thing, surface tension here. This will be 2 pi a s cos theta. Everything will look same, that r, theta. So this is r, that is a. This is theta. From here we get cos theta is a by r.
There will be two surfaces, right?
हाँ, two surfaces होगा into two, since two surfaces. बस so यहाँ पे you'll write rho into pi a square into v square, the water jet का force, in this case air, this is the density of the air, should be equal to 4 into pi a s cos theta. Substitute the things and you'll get the answer. We neglect gravity. So whenever you get these kind of questions, right, dropping, especially from a dropper or soap bubble flying off, this geometry part is what is important. The relation between this cos theta and stuff. This part will remain same. Here mg is pulling it down. Here it is that rho a v square is pushing it down. That is the only difference. All these questions are like similar category. Yeah, we neglect gravity, or else it becomes quite complex. Meaning it will start hanging down and all. Will not get into that. Clear with this? Let's see a good one. These are fine. Matlab, even in advanced, these questions will be like easy to moderate. There. This is a proper question. So we have a capillary of small r on one side, and one side you have a big pipe. Right. So you're pouring liquid from one side. This is what would happen. On the left hand side, this height is h1. So basically, this is capillary. Since the radius is very small, the surface tension will dominate. On the other side, the liquid would be h2. So here it's a big pipe, so you can ignore the surface tension. Like I told you last time, right? When the radius is very, very small, the surface tension actually becomes dominant. So we can ignore the surface tension effect on the right side, but surface tension effects on the left side. And you're pouring liquid continuously. So the question was plot h1 and h2 versus time. Let's get this. This is a pretty good one. Initially, the whole thing was empty. You started pouring liquid slowly on regular intervals. How will the height of the liquid on both the sides change with time? You pour it slowly. There's nothing there. It won't matter. The thing is, you're pouring at a constant rate. That's it. Right. Don't want the liquid to start oscillating. I hope the question was clear. Think. I'll give you another 2 minutes. I'll just give you a small hint. See, initially, the moment you drop the liquid, all the liquid will get pulled in by this guy. The surface tension will dominate inside. So unless you reach a certain height, the liquid will not go into the big container. The 2 pi rs cos theta will pull all the liquid. So initially H2 is 0 for some time. So instead of drawing the, don't draw the graph, okay? Try to draw the situation. For example, let me show you the one situation that will give you an idea how to proceed. Okay. So the moment you put liquid in this, initially what will happen? All the liquid will be pulled out from here. There'll be no liquid here because the surface tension force will dominate. So this is how the meniscus will be. The liquid will only be on the here. Now, if you keep putting more and more liquid, initially all liquid goes into capillary. Because the 2 pi rs cos theta attraction is strong enough, it will pull the water. Now what happens? This will continue to happen till you reach this point. H is equal to 2s cos theta rho gr. Whatever is the values, I don't care. This is the position. Now, if you put any more liquid, now the liquids will rise on both the sides. Now try to draw. Try, I'll give another 2 minutes from here. So initially, the liquid will keep rising on the left-hand side till you reach this position, 2s cos theta by rho gr. Now, if you put more liquid, now remember, surface tension can pull this much height. If you put any more liquid, now the whole thing will rise on both the sides. So try to draw the situation completely, and then we'll see the graph. Because if you don't know what is happening, there's no point in drawing the graph. Think. Currently, your seniors are writing 3 advanced papers per week. 3 full syllabus. Every alternate day. In a month, they'll be done. You are seniors. I'm behind them now, then I'll be behind you guys. You can see 3 papers of the same topic. There are 3 papers of the same topic. Send me the screenshot now once. मुझे भी देखने दो. Send it later. Yeah. Actually, there is one practice paper also. These people wanted last month ka. That also kept it online. Maybe that is confusing, I guess. And I changed the name. You will see on top of it. Mechanics, kinematics to rotation, deadline 18th April. H2 is constant, then starts exponentially increasing. See, this is what happens after this. Now, if you put more liquid, remember you're putting the liquid slowly, okay? Now, whatever liquid you're keeping will be shared by both of them. So this is what you'll notice. Initially, this was the H. this liquid level will start going up. This side also the liquid will start rising now. So this will be that additional x which will rise. So this also will be x, and this will be that initial hk value. You're getting? Now on the left hand side and right hand side, the rate of increase will be same. Whatever you increase on the right side, the same height will increase on the left side, but you already have an extra h because of surface tension. And then you keep pouring more and more liquid. Then what happens? The liquid will completely come to the top. Remember, you'll get a bubble like this. Liquid won't overflow. Liquid will not overflow. Then so on the top you get a bubble like this. So just before popping, the liquid has to reach a certain height. This we calculated in that problem. This problem. So we calculated, right? The height of the liquid level should be 2s by rho Ga. So when this height becomes 2s by rho Ga, at this point, you basically get an outer meniscus. Water won't come out of the hole until you apply enough pressure. If you observe here, the meniscus is like lower curve. Suddenly it becomes an upper curve. Here it was flat. Then if you put more liquid, and now you're done. The liquid start coming out. Now the heights have become constant. You cannot have more than this height now. Spills out. This is your problem 15. Is this whole scenario clear? Please have a look at this first. Now try to draw a graph. Liquid leaks out. This is H1 and H2. H2 has become greater than H1. So luckily, right, in the exam, you'll have options. You can actually eliminate options. H2 should be greater than H1. Initially, H2 will be 0 for some time. So it becomes more easy to eliminate. Drawing a graph is more, a little more difficult. Eliminating is more easy. Now, can you put a graph for this? Try. I'll give you a minute. Put a graph. See. Let's draw both the graphs at the same time. So first, initially, H1, this guy would increase at a faster rate. And during this process, this guy is H2, the green one. So you reach a height H, which is 2s cos theta by rho G R. So up to this instant, right, the water level will not rise. So this is the region where all the water goes into the capillary. Now here, both will increase, but understand something, it will increase at a slower rate. Why? They will increase at the same rate, but they'll increase at a slower rate, because initially all the water coming was going into the capillary. Now all the water is coming is shared between the capillary and the big container, isn't it? So the rate of increase will not be as fast as before. It will increase, but the rate will decrease.
So will the rate be exactly half what the previous was?
Half of what? Come again?
Like if the slope of the first part was 1, then the slope of the second part will
नहीं
be
नहीं
half.
नहीं नहीं नहीं, ऐसा नहीं होगा. बहुत छोटा होगा ना. God, it should be very small, isn't it? The radius is big, right?
Okay,
So
good.
you're sharing water between the big one and the small one, right? So the height will increase pretty slowly actually. Slope actually it will be very small. If you actually ask, it would be something like, if this is the horizontal line, it would be pretty close to this.
Okay.
Almost flattish.
Samjha sir.
Yeah, so rate of increase is less since liquid is shared between both the containers now. The same amount of liquid is going into two containers. Liquid is shared between the two pipes or two containers, whatever you want to call. But we will notice the rate of increase will be same. Because whatever is the heights are not same, rate of increase is same. If the right side increase by 1 centimeter, left also will be 1 centimeter. This will continue to happen. At that point, this guy starts becoming, you will reach the top. At this point, right, water's at the top. Now, at this point, right, this guy will never change. This guy is gone. This is H1. Once you reach the top, you can't go more than that. But during this process, see what happens. So it is increasing, increasing, increasing. Now something happens again. Once it reaches the top, the liquid, right, will start increasing slightly more. Why? Now, because all the liquid is going into one container only, right? You're getting it? All the liquid goes only into one container. So the rate of increase will slightly increase. And this will go up, go up, go up. This will cross this point. And at some point, this also becomes constant. This is the point where the water starts leaking. Liquid leaks. That's your H2 ka graph. The rate of increase will be slightly higher because all the water goes only to the right side. Remember, right side area is pretty big. So it won't really increase that much, but it would increase slightly. The rate of increase of height slightly increases since all liquid goes into right side. Clear? Please check the graph. That's what I was saying. You could have exam it would be a little easy to eliminate the graphs. H2 should be greater than H1. You can eliminate at least one graph. You should know this rate of increase should be same. The slope will change. So that much ideas if you have, right, it works out. Clear the graphs? It's a pretty good question. So H2 ka values you can figure it out. Okay, take a break. Come back by 7-8. We'll continue from here. Any doubts on this? Any doubts so far? Please ask me.
So can we go to the first question of today's class?
Yeah.
In which we take out the capillary. Yes, sir.
बोलो ना.
वो जो bottom meniscus है, उसका जो theta है,
Hmm.
and the top meniscus theta, how will they be equal? How can we say they are equal?
They're not equal, but approximately. I understand your point. We approximate it.
Okay, sir.
Approximate it, हाँ. But it will not be equal. What you're saying is true. But वो सिर्फ question के लिए, right? We approximate it. Or else I had to give you more data.
Okay, sir.
Yeah, yeah. What you're saying is true. It is not same. Any other doubts? Chalo, come back by 7-8. Chalo, switch on your cams. So we have two parallel plates. Let's say this length is L. With a distance d between them. Let's say two square parallel plates. This L is much greater than d, so that we can neglect the edges ka effect. Contact angle is theta. Surface tension is T. So the plates are placed just above the liquid as shown. Find the height of the liquid. So instead of a spherical, thing, you will get a cylindrical surface now. Find H and the net force on each plate. So these plates, right, won't be in equilibrium. Someone has to catch them in order to keep them at rest. So why is that? Others, keep your cams on. So just to give you an idea here, what you get is a cylindrical meniscus like this. So the surface tension force now will be like this now. Able to visualize how it is? It's like it's kind of like this. If you're seeing my screen, the surface would look like this. You getting it? So till now, if you see, right, in that circular pipe, the meniscus was like this, a bowl kind of shape. Now we will get a half cylinder. Two S by rho G D G. Okay. See, this is easy. If you look at the side view there, so this side of the force will be surface tension S into L. Surface tension force will be S into L. Again, we're ignoring that edges there. This is the height of the liquid. This is D. So the surface tension force in the upward direction would be 2SL cos theta. Should be equal to mg, which is rho, length, height, width into g. So this guy would be 2s cos theta by rho gd. Easy. Basically, surface tension force is what? Surface tension into length in contact. So here the length in contact will be this entire length L. So previously it was 2 pi r, now it is S into L. And what about the net force on each side? So if you look at the plates here, you need to understand at the bottom level here, the pressure is P naught. So as you go up, the pressure actually decreases. If you go X from the bottom, the pressure becomes P naught minus rho gx. That means from outside, pressure P naught is pushing, from inside, the pressure is this thing. So there's a difference in pressure. So from outside, the pressure will be P naught into length into H. From inside, the pressure will be pressure at the center of mass into area. Remember, whenever the pressure varies linearly, you can take the center of mass. So center of mass will be where at H by 2. So that would be P naught minus rho g H by 2 into LH. So the net force will be rho g L H square by 2. P naught will cancel out. That means someone has to apply an external force. If you don't apply external force, this is what will happen to the pipes, the plates. The plates will become like this. Because outside the P naught is more, inside the pressure would decrease. So here it is P naught, here it is P naught. So as you go up, the pressure would be P naught minus rho gx. So the plates will actually come closer like this. So someone has to apply a net force in order to keep the plates vertical. If there is an external force, plates will become like this. The plates would tilt. Clear? So as you go up, the pressure actually drops. Remember, we did that thing concave, convex. If you see here is P naught, here the pressure is less than P naught now. Any doubts on this? All got this? Let's see a better version of this. This is like a standard one. Same question, but what if
Sir, in the previous question,
Mhm.
we can't say
No,
that
no.
S into L is the force.
But contact angle भी है ना रे. The surface tension force will act at an angle like this, na?
No, on the plate.
Plate में okay, हाँ. I got your point. तो बोल रहा हूँ ये भी include करेंगे. Yeah, we have to include that also. What he's saying is true. ये भी theta होगा. So there'll be a vertical horizontal component SL sine theta. You're right. Minus SL sine theta. You have to include the surface tension ka force also in the horizontal direction.
So how is it in that direction?
You're taking horizontal forces.
No.
Pray gods.
I
If
mean
the
that it should be in
liquid
the opposite
is-
direction, no?
Oof, you're drawing FBD of what? The liquid or the plate?
Of the plate, sir. Should pull
The
it
liquid पे
inside, right?
कैसा होगा?
So liquid pay, it will be on the outside. So plate pay
तो
should be on the
plate पे
inside. On the inside.
so what did I do?
Oh, I'm sorry. I thought of the ulta banana. Sorry.
Yeah. You're getting on the liquid, it is outside. So plate पे it should be inside now. So this is the SL, right? Is that getting it? We have to include that also. This is the surface tension force on the plate.
Vertical load is only the horizontal component. No?
Sirf horizontal component, no? Because we are vertical, तो we are assuming somehow it is balanced. This is just the horizontal force.
Okay.
So add कर लेते हैं F net horizontal. That's what you're saying, surface tension का component. Yeah. All clear with that? We have to include the surface tension also because वो theta है. If theta was 0, right, that wouldn't have come. Right. So let's say the same thing. We have two parallel plates, but this time they're at an angle here. Let this be angle alpha. This is length L. And if you see the liquid here, liquid actually becomes like this. You're getting how is the shape? The surface tension is S. Contact angle theta. So we have two plates are touching at one corner. With an angle alpha as shown. So what I want you to find, if you look at this line now, find equation of that surface. And you can try this as a homework, find heat produced. So you can see the liquid surface here, how it is. So what he did not see what here, he kept a rubber band here and he kept a paper clip here. So you got a thin gap there. If you look this from the top view, it is like this. So the rubber band is keeping it close and this paper clip is creating a space. So that is how you got the gap. He kept a paper clip in the middle. So this is blocking the plates from getting closer. That is how it was like. The shape would be like an arc. Find the equation of that surface. in x and y direction. Okay, we don't want a 3D equation. Get me the equation in terms of x and y. See, you don't need to indicate or do anything. So this equation which we have, let's assume this is your x-axis. Take a small dx here. So if you take a small dx here, we get a piece like this. Right? And let this be the height y. So basically that's your x and y coordinate at any point. So on this small piece, if you look at the surface tension of force, that would be like this, which is s into dx. We'll take the vertical component. And remember, this length will be how much? That length will be x into alpha. This length is alpha. So that width would be x into alpha. And this length is dx. So here also surface tension force will be like this. So if I just draw that piece again, so the surface tension force is like this. The surface tension force is like this. And this is basically balancing the weight mg. And we know this angle is theta with the vertical. This was theta. So the vertical component would be 2s dx cos theta, right? That should be equal to mg. So 2 times s dx cos theta, mg will be density. Height of this thing is y. width is dx, the other side is x d theta, x alpha rho vg. Clear? Then if you equate this, what do you get? From here, dx will cancel. We end up with x into y is equal to 2s cos theta by rho g alpha. You're done. So therefore, we got x into y is some constant, where x and y are the coordinates. Basically, on that curve which you are taking, this is x and y coordinate for any point. So we can choose this bottom as origin. This point is x comma 0. So you took a point at a height y. So we're getting xy is constant. This shape is a hyperbola. Clear? That is the equation of that curve. How to find heat produced? For each section, find the work done by surface tension. For each section, find the change in potential energy, which is mg y by 2. The difference will be heat produced. That you can give it a try. Have a look at this. So this width is x alpha. This width is y. And this guy is dx, length, breadth, and width. Length, breadth, height. Yeah. There. That's about the surface tension. Alpha is a small angle. Yeah. Yeah, I think it should be small. NATO actually won't get enough height. Remember, the radius of curvature should be small. Clear. The next thing is elasticity. So make sure to go through this entire thing. We did almost 18 questions, meaning in that we did some pretty good ones also. Chapter is not that big. So viscosity, surface tension, all these are small ones. The next one is elasticity. We'll finish with the introduction today at least. Actually, इसका little introduction now. Remember this with in thermal expansion, the force between two molecules. So whenever you have two molecules in a lattice, this is the diagram between the force versus distance between them. We have done this in thermal expansion. So if you have two molecules, 1 and 2, when the molecules are little far, the nucleus 1 attracts the electrons of molecule 2. So therefore the force is attractive. If you bring them too close, the force becomes repulsive. So this particular distance here is called the bond length. At this point, you have a maximum force of attraction. So if you try to push them closer, the repulsion will dominate. If you try to push them apart, attraction will come. So either way, they always try to stay in that particular bond length. Do you guys remember this page? In thermal expansion, this was the concept we did in thermal expansion. And then we said, because of this reason, whenever you increase the temperature, the length would increase or decrease. Have a look at this page once. So it is the same introduction here for elasticity also. Clear? So now, We don't need this page actually. So this is what results in, so whenever you try to elongate or compress a body, there are internal restoring forces. So when a body is deformed, deformation meaning elongation or compression. So internal restoring forces are generated. Look at the word internal, they're inside, restoring. These forces will try to bring you back to normal state. That's a technical name, but this is nothing but tension. The tension in the rod, the tension in the string, these are the restoring forces. Internal restoring forces are generated which try to bring the body to natural state. So be careful. What we are interested in this chapter is tension, not the external forces. So this property, right, to resist a deformation is called elasticity. So whenever you try to stretch, it will oppose you. Whenever you try to compress, it will oppose you. So this opposition, this property to oppose the deformation is called elasticity. And why does it oppose? We saw at a molecular level, that's what happens. Everything wants to be at a particular bond length. You try to get closer, the molecules repel, the nucleus repel. If you go too far, the attraction is more. So this is where a thing comes. So which is more elastic, steel or rubber? So elasticity, right, is one of the most misused word. People think elastic matlab easily stretch hoga, but actually it is the other way around. Yeah, steel is more elastic. Rubber is more stretchable. Somewhere down the line, the word was misused. This is a CT equation, which is more elastic. Remember the definition of elasticity. It is a property to resist a deformation. If you take steel and rubber, steel is more difficult to deform. So be careful. Elastic doesn't mean it will stretch. Elastic meaning it is more difficult to stretch. So steel is more difficult to deform than rubber. Therefore, steel is more elastic. If you remember, we discussed these things, in collisions. What are plastic bodies? E0. Basically, these things do not generate any restoring forces. If you push them, they just stay like that, like chapati ka dough. If you deform, the deformation will just remain there. They'll not try to come back to natural state. Such materials are called plastic, or they can say the metal is behaving plastic nature. Other than this, we also have some properties. When you say material is brittle, means what? They will crack and they're difficult to stretch. Example is glass. The reverse of this is ductility. When you say a material is ductile, they can be made into thin wires. They can stretch. Like example, copper. That's why we make copper wires. What is malleability? They can be made into thin sheets. Yeah. Quite an important chapter if you're a civil or a mechanical engineer. So remember in fluid mechanics, right? When we studied, see, NLM, when you studied everything in terms of force and mass. When you studied fluid mechanics, you studied everything in terms of density and pressure. In place of mass, you studied with density. In place of force, you studied with pressure. Same way, when you study elasticity, right? Instead of studying in terms of force and elongation, we study something in terms of stress and strain. It's like, let me ask you this thing. How do you compare, let's say, if I say the bones of an elephant and the bones of a rat, which is stronger? Now, the problem people will say elephant, but that's a very wrong way of comparison. You cannot compare two different things of same thickness. What you're supposed to do is, if suppose you're taking, definitely see, an elephant ka bone is more difficult to break compared to a rat, but that is because it has more thickness. So let's say you're studying different kind of animals ka strength and you're trying to study the structure or anything. What you're supposed to do is not the force required to break, you study force per unit area. Meaning if the elephant and the rat are of same size, will the bones be similar? If you actually think about it, if you make the rat the size of an elephant, you'll observe the rat ka bones are thinner compared to the elephant. As the size of the animal becomes bigger, the bones have to be more thicker. So what you do, you study force per unit area. So you take a rat ka bone and let's say you apply some pressure and see till the point till it breaks. So you study the force required per unit cross section. You do the same thing for elephant. You do the same thing for maybe a tiger, 4 or 5 animals. Generally, what you observe, the ratio will remain same. So this tells us the composition of the bone is same for all the animals, even though the sizes are different. But for example, let's say the rat ka bone F by A is bigger than elephant. That means somehow the rat ka bone is made of a different kind of structure or a different composition. You know, then certain humans, right, they have a certain gene defect. Their bones are more denser. They have like 3 to 4 times more calcium. So their bones are almost have a more density. These people, right, when they fall down from first floor, second floor, their bones don't fracture. Very few people in the world have such kind of, you know, it's a kind of a abnormality, but these people have difficulty swimming. The bone weight is too high, they have a problem in swimming, right? So there are some people with that kind of issues whose bone density is much higher than normal humans. So their structure is built differently, right? So let's say, so whenever you study about strength of a material, you just don't take this material, you take force per unit area. So consider that is how you see strengths. So if you consider a body in equilibrium, so let's say we have some body here, you are applying a force F1, F2, F3, F4. So if you cut the body into half and let's say you draw FBD of an half, let's say FBD of the left half. So you will observe at the cross section, the tension will be in some direction here. So we have a force perpendicular and we have a force parallel. So on the cross sectional area, the restoring forces will have two components. So one component of tension will act parallel to the surface, one component will act perpendicular to the surface. So we define something called longitudinal stress. Which is F perpendicular by cross-sectional area. So this is one more thing. So whenever you're studying structures, right? Structures have different kind of stresses. All are not same. And the second thing we define is called shearing stress, which is the F parallel by cross-sectional area. Both are completely different. I'll give you some examples on it. There's also a third type of stress called volume stress. Let me show it on the next page. Think of like this, you know, when you stretch a paper and when you tear a paper. When you tear a paper, what kind of stress is there? When you're tearing a paper, right? If you look at the no, think of like this thing. See, if you look at my screen, right? When you're tearing the paper, what you're doing? If this is the paper, right? You're tearing like this. When you're tearing, can you see what area you're talking about? You're talking about this area, isn't it? And the force applied is this way, and the area is this way. The force is actually parallel to the surface. So tearing a paper requires shearing stress. But if you stretch a paper, when you stretch a paper, you're talking about this area, right? If you take something more thick, see, if you take this book, when I try to stretch this, you are applying force on this area, and the force is this way. Force is perpendicular to the area. So stretching a paper requires longitudinal stress. If you try to tear the paper, it requires shearing stress. Getting it? So if you take a paper is more difficult to stretch, right? But easy to tear. So paper can withstand longitudinal stress, but cannot withstand shearing stress. If you take a plastic, a plastic bag, plastic sheet, it is more easy to stretch, but a plastic cover is more difficult to tear. Ever observe your biscuit packet or something? If you don't exactly cut that openings there, that's where they give grooves. If you try to tear somewhere, a plastic sheet is very difficult to tear. So plastic can withstand shearing stress, but cannot withstand longitudinal stress. So every material has a different property. If you're pinching your sister or brother, that's a shearing stress. So pinching is shearing. Human skin, right? It is easy to make holes, but it is very difficult to, pull the human skin. It's very difficult to tear. You must have seen this, right? Guinness World Records or some people, right? They actually put hooks and hang. Never seen. I'm going to show some graphical images, so don't get scared.
So in that example, if the vertical components of the forces were equal, there wouldn't have been any shearing stress, right?
Which question? Which part you're talking about?
That F3, F4, that one which you just drew.
Meaning I just drew some random diagram. Right?
Yeah, so if the vertical components were equal in magnitude, there would be no shearing stress.
They
right?
wouldn't have been. Right.
Okay.
There, humans can. It's. This is what I was saying. Now, if you ask her why they do this, I have no idea why they do this, but that's what I was saying. You can lift the entire human weight with this. It's very difficult to tear. So I'll delete this page.
Yeah, please, sir.
Clear? So let me take an example of this thing. So there's also a third type of stress called volume stress. This thing comes, whenever you're trying to compress a body from all directions. So this is volume stress. This is actually same as pressure. This is force perpendicular to the surface area. Now be careful. If you look at all the three formulas, they look the same. Longitudinal stress, F by area. But which force? Perpendicular to the cross-sectional area. Shearing stress is F by A. Which force? F parallel to the cross-sectional area. Volume stress, F perpendicular to surface area. You're getting the dimensionally all will look same, but three are completely three different properties. So if you try to take a paper, and if you apply force on this, this is the area we're talking about. So stretching a paper is longitudinal stress. So every material has different capacity for longitudinal, different capacity for shearing stress, like paper and plastic. Paper cannot withstand shearing stress, but plastic can withstand shearing stress. Same thing if you take the paper here. So if you're trying to tear the paper, we are talking about this area here, and the force applied is this way. You getting how is this? So tearing a paper is shearing stress. So in your house, can you tell me where is the shearing stress and where is the longitudinal stress in the building? I'll give an example. There are beams and there are pillars. Isn't the main structures? Whenever you construct a house, there are only two things. There are beams and pillars. Baki beach mein the wall and all is just a filler. That's the reason if you see, right, if you want to make a hole or something, they'll tell you, you can't make a hole on a beam or a pillar. You're not supposed to make a hole on that. You can make anywhere else, wherever you want. You can break the wall. You just can't touch the pillar and beam. Technically, if you see, a building is nothing but beams and pillars. That's it. There's only two structures. Everything else is just a filling gap. So you tell me, beams and pillars, which has longitudinal, which is shearing?
The friction between them will be shearing.
Friction. If you take a pillar, right, what is the pillar trying to do? Support the weight, right?
Yeah.
The entire mg is pushing, right? It's trying to compress. So pillars have longitudinal stress. What about the beam? If you look at the beam here, this is the mg. This is the area of cross section, isn't it? The beam is being pulled apart, isn't it? If you look at the beam, it's just like paper only. The mg is this way, and this is the area of cross section. So beams have shearing stress, pillars have longitudinal stress. That is the reason if you see the construction, right, they use more steel in beams and less steel in pillars. Because concrete has a problem. You can compress concrete, it can withstand any amount of force, but the moment you try to pull concrete, it will break into pieces. Concrete can withstand compression, but cannot withstand elongation. Whereas steel can withstand compression and elongation. But the problem is, concrete is cheaper. 1 kg concrete will cost you like 4 or 5 rupees. 1 kg steel will cost you 200, 300 rupees. It's quite expensive. So whenever you're trying to put a building, wherever you know there is only compression, people use concrete. Wherever you know there is a more chances of shearing stress, they use more steel. So it is a thing between cost and the weight and the construction. There are multiple things. That's the reason whenever you build skyscrapers, right, people don't use concrete because if you more concrete, it becomes more heavy. Ever seen Tom and Jerry? In that the building is made of all rods ka construction. The entire building is just of rods. Tom and Jerry are running on the rods. Ever seen that? The entire building is just a skeleton made of steel rods. Thick rods. Generally, that is how it is built. The beams and pillars are made of steel rods for skyscrapers so that the weight is less. So if you use concrete, the building becomes too heavy. Petronas Twin Towers is there, Malaysia. Seen those things, the 2 towers? Yeah. So those towers, right, the Malaysia had a problem. They had a budget problem. They couldn't use so much steel. It was becoming too expensive. So the engineers did something. The weight of each building is, I think, 2 lakh tons. Huge weight. So skyscrapers are quite heavy. So that is one. I hope now you got an idea about shearing stress and this thing.
So, but pillar में भी तो weight होगा, like why is the
Which one?
Yeah. Like in the pillar also there'll be shearing stress, huh?
A little, especially on the connections. No? Whenever you're connecting a pillar to the beam, that is where the shearing stress comes.
Acha. Okay.
But if you're just pushing it down, there's no problem with that. So if you see here, now tell me one thing, ever seen metro ka pillar? Now think about it. Metro ka pillar and you're building a pillar, your building is more heavy than that thing. Logically speaking, at any point of time, pillar ke upar 1 or 2 compartments will be there, isn't it? That's it. But metro ka pillars are very thick. Compared to your building ka pillar, metro ka pillar is very thick. Why? Can you tell me what kind of stress is there on Metroka pillar? High speed, that has nothing to do with it. See, the train is going at high speed. Why will the weight vertical component mg change? Plastic can stretch, but difficult to tear. Metro is moving due to friction, right, Ishan? See, next time observe, when a train is going on this, the Metroka pillar which is there. So if the train is going forward, what is the direction of friction? It is also forward, drunkards. Friction is only making the train move. It doesn't oppose the motion. The reason the train is moving is because of the friction. When you're walking, the friction is in the direction of motion, isn't it?
Yes,
Which force is moving the train? Engine force, special force, speed force. There's nothing like that. When you're walking, the reason you're walking is because of friction. That means if a train is going here, this is the friction. So about the central axis, if you see, there is a torque. Metroka pillars are being twisted. Every time the train goes, the Metroka pillar is being twisted. Isn't it? If you see the side view, this is the pillar. When the train goes here, the friction will be here. This is the perpendicular distance d. So torque is F into d. And the friction is quite large. You're pulling the entire train. And it doesn't happen once. Every day the same pillar is being twisted something like what? Every time the train goes right and back, front and back, that is 600 to 700 times in a day. The pillars are being twisted. And later on, I'll show you. Actually, I already showed you this. In SHM, remember this torsional pendulum? I taught you this. Torque is pi eta r power 4 by 12 theta. So if the radius is more, it is more difficult to twist, isn't it? So later on, we will going to prove this later on. Yeah, they'll be on the other side also. No, gods. On the same side, when the train is going this way, this friction will be this way. It's a couple. Both the frictions are rotating in the same direction. Or do you mean to say both the trains will go like this? Yeah, they go in the opposite directions.
Sir, what I was saying is that if there is one train, it will go from the center of the pillar, right?
No, that's the monorail.
As a monorail, then there will be no torque now.
There is also torque there. The thing, right? The pillars are not exactly point objects, na. Even if it goes little to the side, still isn't there a perpendicular distance? The friction is not exactly acting on the axis, right? And if you look at the pillars, observe that the tracks are somewhere here. They're not exactly on the top of the pillar. If you keep exactly on top of the pillar, you can't fit two trains on the track.
So there are two trains on the pillars. I thought there's one train.
Metro mein one train will not be there. Already the two trains only are not sufficient. Clear? So Metroka pillars, right, have a lot of shearing stress. Metroka pillars are being twisted. That's why the pillars are more thick compared to your building. Clear? So I can write that down also. So next time when you see a metro pillar, now you understand why it is so thick. Because it is not trying to balance the weight of the train. That is easy. Uske liye itna bada pillar nahi chahiye. Problem is you're trying to twist the pillar and that is creating a problem. Twisting creates a lot of issue. So this is the friction due to the train. And if both the trains go at the same time, you'll get double the torque. Normally for a metro, right, the life expectancy is around 50 years. You're expecting that pillars will technically 100 years, but then we know now how we use them. So yeah. So even if you design them, let's say for 70, 80 years, that means every day the pillar is being twisted like 600, 700 times for 50 years. Imagine the kind of stress. So you have to, and anyway, we over engineer them. If you need radius R, they make it actually like 3.2R or 2R. So metro rail pillars, right, are under shearing stress. There is also longitudinal stress, but shearing stress is the main thing we are interested in. The pillars are twisted by the friction. So when you're standing, your legs are having longitudinal stress. Whenever you're taking a turn, there's a shearing stress. And the weight creates longitudinal stress. That is actually little. So that's a little about introduction. So next class when we catch up, right, we're going to study Hooke's law, where we'll study about Young's modulus and all that stuff. It's a small chapter. We should wrap up in 2 classes. And then we will start off with gravitation after this.
So,
हाँ
so
जी.
basically only when it's turning, there's a torque.
Turning मतलब
Matlab when
train
the
का
train,
बारे में.
yeah.
No. When the train is going, there is a torque.
But then, so how can one friction be opposite to the other?
Because this train will go this way, this train will go this
Oh,
way.
acha, you're still taking 2 trains. Got it.
Why you guys want to design a metro with 1 train, Ray? Which kind of city is that? But just imagine, you build a city, Ghatkopar to Andheri, 1 metro. मतलब पता है कैसा होगा? Until this train goes and comes back, people in Ghatkopar are just waiting. Just imagine, वो train Ghatkopar to Versova जाके Versova to वापस आएगा, then people will get into the train. मुंबई में चलेगा? You guys are obsessed with making 1 single train on the track. You guys are very bad civil engineers.
But you're ignoring the